Hello and welcome to the LUniverse Virtual Planetarium from Lancaster University. The following is a recording of one of our free live public shows that we ran during early 2021. I hope you enjoy.
Let's start with the observation of the planets. Unfortunately, it's hard to see many planets and this month, but another unfortunate thing is that the day is getting longer and longer. But one of the planets that we could see is Mars over here, which is right above of Orion. Over here is Betelgeuse, the orange giant of Orion, the top left star of Orion, and above that is Mars. Now, as the month goes by, though, Mars is moving closer and closer to horizon. And another exciting thing about the planets for this month is taking place on the 28th of May, where Mercury and Venus pass very close to each other. But it's quite tricky to see it as the sun doesn't set or has just set on that day. Now, if you're attempting to observe those planets with a pair of binoculars, please be very careful, as the sun can seriously damage your eyes. And I would suggest just wait for the sun to be completely gone before you start looking for the planets on the night sky. Now, mark your calendars. So the 26th of May, we will have a supermoon. And what do we mean by a supermoon? The orbit of the moon is not exactly circular, but it's an ellipse. So basically that means that the moon sometimes is closer to the Earth and other times farther away. Now, that supermoon takes place when we have a full moon to a really close distance from the Earth. And just to see, just to give you an idea on why we're calling it a supermoon, that's because it's up to 14% bigger and 30% brighter than a full moon when the moon is on the farthest distance from the Earth. Now, this shouldn't be confused with the optical illusion, which makes the moon looks big when the moon is really low on the horizon or in between buildings. You most probably have seen that in like big cities, for example, Manchester or London. When you see the moon right in between buildings, you can see that it's huge. But when that moon goes up in the sky, then you see that it's not as big as you thought it will be. Just to recap, the supermoon is a real thing, and it depends on the orbit of the moon around the Earth, but the phenomenically bigger moon on the horizon is just an optical illusion. Now, the best time to look for the supermoon is just after moonrise or just before moonset. And the moonrise will be at 11 p.m. on the 26th of May. Mark your calendars. And this month, we will have another meteor shower. The Ita Aquarius, which is associated with Halley's Comet that visits Earth every 75 to 76 years. The peak of this meteor shower is actually tonight, between 3:45 and 4:30 a.m. You can potentially see up to 50 meteors per hour, but realistically, you're gonna see much less than that. You can locate that meteor shower between east and southeast, is over here. But go for it by all means, but don't be disappointed if you don't really manage to see anything. It's because it's quite challenging, as it's also near the horizon, and it's only visible for just 1 hour. Now, with that out of the way, I am giving the stage to Jim to tell us all about almost all about Aurorae.
So let's get going then. So hi everyone. Yeah, my name's Jim Wild. I'm one of the researchers at Lancaster University, and so I'm just going to talk a little bit this afternoon about the Northern Lights, or the Aurora Borealis, and just a bit about what they look like, some of the stories behind them, and then a bit about the science that we try and do to understand what makes the Northern Lights and why they look so special. And so one of the things about the Northern Lights is it's on a lot of people's bucket list. A lot of people want to see it, and so there's an awful lot of you'll find an awful lot of calendars and a lot of postcards with absolutely magnificent photographs on, and just like this one on my first slide. And actually, it's an art form, taking photographs of the Northern Lights like this. So I've borrowed some from really good photographers from around the world to kind of show you what the Northern Lights might look like if you're lucky enough to see it. And when people think about the Northern Lights, this is the picture that usually springs to mind: these sort of curtains of green smoke-like ghostly light in the night sky. And actually, you often think about scenes in cold places with lots of snow and ice. And here we have a beautiful image of the Northern Lights over an Arctic fjord with the snow on the mountainsides. And we've just been hearing about the moonrise, the supermoon. Well, there is a full moon in the top left-hand corner of this image. So if anyone out there is interested in photography, you might start to think about the technical challenges of trying to take a picture with a bright moon and some quite faint lights. And really beautiful photograph here of these green ghostly lights in the night sky. And although the most common color of the aurora is this greeny color, they do appear in a variety of different colors and shapes as well. And so in my next image, I've got another green aurora, this time over a lake environment, and you can just start to see the different kinds of shapes you get in the aurora. Now you're going to find that I start using the words Aurora Borealis and Northern Lights so interchangeably. So I'll just get that out of the way to begin with. So the Aurora Borealis simply means the northern dawn. It's a mixture of Greek and Latin, and it comes from a time when the lights of the Northern Lights would be seen. They would look a bit like dawn, starting about like the sun below the horizon, lightening the sky, but they're in the wrong part of the sky. The sun rises in the east, and the Aurora Borealis are off to the north usually. So we get this same, the northern dawn, the Aurora Borealis. And there is also the Aurora Australis, which are the southern lights, and I'm going to get to those a little bit later in my talk. So if you hear me saying Aurora Borealis or Northern Lights, they're just interchangeable words for the same thing. Now, the one we're looking at right now is I think really beautiful, because you can see just how very clean and crisp the edge of this band of auroral light is, that's stretching from the horizon all the way overhead. And it's bright enough to be casting a reflection in the lake, and it's bright enough to be seen through light pollution from a town there in the distance. So the Northern Lights can be incredibly bright, and they can have these very sharp features, very sharp edges, and other times they're much more smoke-like and almost cloud-like in appearance. So there's a huge array of different kinds of shapes and structures in the Northern Lights. I've already mentioned that they come in different colors, and so here is a display of the Northern Lights that looks quite different to the one we saw in the last photograph. So in this one, for a start, the sort of the band of light is broken down into rays or shafts of light which seem to be coming down from a point in the sky, and you can very clearly see that the color changes from that green color to the red pinky color. So that's the other very common color in the Northern Lights, that reddish glow. Now, if you're ever lucky enough to go somewhere where you might see the Northern Lights, and I'm going to talk in a little while about where the best place is to go and see them, you might see something in the sky, and it's sometimes hard to tell exactly what you're looking at. I think if you were looking at what we're seeing in this photograph, you'd know you were looking at the Northern Lights, but sometimes they're very faint, and you're trying to work out, are you looking at a patch of light, or are you actually just looking at perhaps a little bit of wispy cloud that's reflecting some light from the ground? And one good way to tell the difference between the northern lights and clouds, for example, is that you can perhaps just make out in this photograph, if I move my mouse, you might just make out we can see some stars through the aurora. Now the aurora are actually they're transparent, so you can see through them. So if you can see stars in the background, that's quite different to a cloud, which is opaque. You can't see through a cloud. So one good way of telling the difference between the Aurora Borealis and a cloud is that you can see through the Aurora Borealis. Now you might be thinking, that's crazy, Jim. I can tell the difference between some green and blue light and sorry, some green and red lights and a boring grey white cloud. Well, what's interesting is that your human vision is much more sensitive in monochrome, in black and white, than it is in color. You require many more photons of light to be able to determine color. So actually, in very low level faint aurora, it might well appear as a gray cloud-like shape rather than having that bright color. And so actually that having that trick of looking through and seeing the stars behind is actually quite useful. It's only when there's enough light coming through that your eye starts to detect color. So very faint auroral displays often look quite smoke-like and gray in color. But they do appear on fewer calendars and postcards. It's usually the really beautiful ones that make it onto those. So one of the things about the Northern Lights that you really can't escape from, though, is that part of their beauty is in their motion. And so here's a fantastic bit of time-lapse video, which I hope is coming through okay, showing the Northern Lights over in Finland. And again, you can see here, you can see the stars appearing behind the Northern Lights. You can see through the Northern Lights and see the stars. And often when you see movies or you see films on YouTube or on the television, this is how the Northern Lights are presented, this sort of dancing lights skitting across the night sky very quickly. But you can see from the motion of the clouds in these videos, and also the motion of the stars in the sky as the Earth is rotating in space, you can see that this isn't a real-time video. So what these videos are really good at is they really demonstrate just how much change you can get in the Northern Lights over time, how the patterns shift across the sky. But also they give an impression of a speed of motion that isn't quite right. And so the other thing I like to try and show people are videos of what the Northern Lights might look like in real time if you were stood there. So this next video is actually a little bit more subtle. I'll hit play on it in a moment, but here we see the Skaggerfoss waterfalls in southern Iceland. And over them, we've got an auroral display. And if I set this video running, I'm hoping the video is coming through okay. You can see the waterfall falling, I hope. You might see some figures in the foreground moving. But the Northern Lights are also moving. They're moving very gently. They have a very swaying, ghostly motion. It's very, very subtle, very, very gentle. And that's actually the kind of dynamics you would see if you were looking at the Northern Lights with your own eyes. So they don't zoom across the sky usually in quite the way you see in those time-lapse films. It's much more subtle. It's much more beautiful. And I've got another movie here of some red and green aurora, and you can see shafts of auroral light coming down from the sky. And you can see perhaps just make out that they are slowly shifting over time. Their position and their brightness is changing over time. Some bits weaken, some bits brighten. And that's generally what you see. You see this very gentle motion of light in the night sky moving across. And you can see from these why they take upon this sort of quite ghostly, almost spiritual appearance. And it's not surprising that lots of stories have emerged about what we're actually looking at. Now that's the kind of view you'd get from the ground, but I just wanted to take us on a bit of a trip into space for a moment. And I've got a bit of an unusual image on the screen at the moment. Now, I'm sure most people will immediately realize this is some sort of map of the Earth. You can make out in the center of the screen the continent of North America stretching from Alaska round over Canada, over towards the east there as I go, and we can just make out, if we continue across the ocean, we have Greenland and Iceland, and you can just make out the British Isles poking at the top here. So we're basically looking down on the North Polar region from a spacecraft. Now this obviously isn't a photograph because the colors all look a bit wonky. So what we're looking at here is a measurement of the Northern Lights, an image captured with a special camera that records in ultraviolet light. So the same kind of light we get from the sun that can give you a suntan, you can't see it with your eyes, but the aurora, the Northern Lights, emit ultraviolet light as well as the visible light we can see. And this is actually a photograph of auroral emissions taken from a spacecraft over the Northern Polar region. Now, on the left-hand side of the image, this sort of orange color, it's been false colored. Ultraviolet light has no real color. We can't see it. So it's just been given an orange color coding, and the really bright colors show where there's lots of ultraviolet light. And on the left-hand side, this is the side of the Earth which is being illuminated by the sun, and some ultraviolet light is scattering off the atmosphere towards the camera. But what you can also see is the part of the Earth that's in darkness. You can see this ring shape, and that's what we call the auroral oval. So when we stand on the ground, we see what's over our head, and these aurora are occurring at about 100 to 200 kilometers above our heads. However, we can only see as far as the horizon, and what you get from these kind of images that we're looking at now is this view of looking down from space. The ultraviolet light of the aurora is showing where the aurora is sitting in the sky, and there's this huge ring surrounding the North Magnetic Pole, so spanning thousands and thousands of kilometers. And so when we see the northern lights over our head, we're getting just a little snapshot of the local view of what's actually a planetary phenomenon. And if I actually take a view from the same kind of satellite instrument, but now the satellite is flying over the Pacific Ocean, you can just make out New Zealand and Australia in the bottom left very easily, I'm sure. You can see that there's this crown-like glow over the southern magnetic poles and also up over the northern magnetic poles. And so what we're seeing side on here is the northern lights, the Aurora Borealis, and the southern lights, the Aurora Australis. And exactly the same process is going on in both places to create the northern lights. Now, most people don't talk about the southern lights very much, but they are absolutely equivalent to the northern lights. So what's going on there? Well, it's a bit of a bias, really. If we think about who lives and where land is populated, in the northern hemisphere, we find that there are lots of indigenous people that have been for tens of thousands of years who live under this region where you can see the northern lights. So at night time, if you imagine you're a nomadic reindeer herder like the person in this photograph, at night time you set up camp, you have a tent, you're outside. If it's clear in the northern regions bordering the Arctic Circle, you would see the northern lights an awful lot of the time. So peoples in that part of the world would be used to seeing the northern lights. And in fact, if we think about who lives in that part of the world, you have the Sami, the Inuit, the Lap, all sorts of different groups of people who all have their own legends and stories about what the northern lights were. And that's exactly the same as in any culture. You build the seasons, the weather into your local belief system. And so you can see in the northern hemisphere, there's lots of people talking about the northern lights. In the southern hemisphere, that ring of auroral emissions, the auroral oval, is actually centered on mainly Antarctica and ocean. So there's no one living there. So most of the time, there's nobody to see the southern lights, where there's lots of people to see the northern lights, which is why there tends to be a bit of a bias, and we hear a lot about the northern lights. But everything in terms of the physics is identical in both hemispheres. And some of those legends are pretty amazing, really. So I've just got another one of these beautiful movies of the aurora moving in real time. And what the legends often talk about, we're looking at the souls of people who've gone into the next life or into the afterlife. So people who've died, often people who've died in either very adventurous or unfortunate ways. So people who died in battle and they're carrying on battle in the afterlife, or these are the gods sporting in the afterlife with some sort of heavenly game, and what you can see is the lights of their battles. Or they may be the souls of people who've died accidentally, or who've met a nasty end, and they're unhappy and restless in the next life, and they're signaling to their families and the people who've been left behind. And most of the legends tend to think it's a bad idea to taunt the northern lights. So whistling or singing at the northern lights thought to be a bad idea, and if you're not careful, the northern lights may come and take you up and either take you off into the next world or top your head off, or something nasty happening. So you'd clap at the northern lights to scare them away. And that idea that the northern lights feed into imagination and culture goes right on up to modern times. So here is a lovely auroral arc over a church in Iceland. So we call them arcs because it's this shape, this curve-like shape. And that's actually a movie. There's a movie running there. It's a very stable arc. It's sitting very still, and it's sitting over this church in Iceland. And if I just now change the image, Here's a painting from the last century of, or sorry, the century before last, the 19th century, from a Danish painter known as Harald Moltke, who went on an expedition to Greenland, and he saw the Northern Lights and tried to capture the Northern Lights here in his artwork. So here you can see he's got most of the details right. He's got the red and the green color about right. He's got this striping effect that we saw in some of those movies, and we'll talk about in a minute as well. So he's really captured the Northern Lights there in his artwork. And right up to today, the Northern Lights feature heavily in our imagination. So we know there have been novels written about the Northern Lights. So the Philip Pullman book, The Northern Lights, unsurprisingly, included the Northern Lights as a key part of the story, and they were sort of a bridge between different worlds, and made into a TV series very recently by the BBC, very popular TV series with the Northern Lights in. And you can see it in Disney, you can see it everywhere. So the Northern Lights appears all over the place in modern culture, just as it has in cultures going back thousands of years. So this is my last bit of artwork for a while, and I'm going to put it here because this is a painting from the Middle Ages of the Northern Lights over a city, and it's trying to show. I like it because it says to me that the artist is really thinking about what made the Northern Lights. So in the bottom part of this image, you can see the city or the town with all the houses, and then above that there are the clouds, and the stars are embedded in the heavens, in the clouds. And then above that, there's another mysterious layer of sort of heavenly light. And here it's sort of portrayed by sort of heavenly candles, which are a bit shining light, and they can be seen from the ground. And we look at it now with modern eyes, and you might think it's a bit fanciful. But the way I like to think about it is that the artist perhaps was really thinking about what he or she was seeing. So remember how a little earlier on I'd already said that the Northern Lights are not opaque; they're transparent. You can see through them and see the stars behind them. Well, the artist here has clearly captured that from the ground you could see the stars and the Northern Lights. So he'd figured that the Northern Lights might be actually behind the stars. That's why you can still see them. So I like to think that even though this isn't quite what we think is happening now, we don't think at the moment that there are candles up in the sky that give us the Northern Lights. The artist was trying to think about the ordering of things in distance away from the ground, because he or she could still see stars shining even when the Northern Lights were shining. So I like to give him some credit for that. But what we now know is that the Northern Lights are caused by the fact that our planet sits within a wider space environment, and a lot of the more recent work is being pioneered by this gentleman here. So this is Christian Birkeland, who is a Norwegian scientist, and at around the turn of the 20th century, so the early 19th century, he'd been undertaking voyages up to the high Arctic and had observed the Northern Lights. And had seen that when the Northern Lights were out, that his instruments he would use for navigation and measurements of the Earth's magnetic field went absolutely crazy. And he worked out that he theorized that the Northern Lights were an electromagnetic phenomenon. And so they must be caused by electricity and magnetism causing somewhere close to the Earth, causing this light in the sky. And he went back to his laboratory and he built a machine which he called a Torella, and it looks like a fish tank on a trestle table, which is sort of what it is. It's a big thick glass vacuum chamber, so you can pump the air out. And he has a model of the Earth inside, which is magnetized just like the real Earth. And he passes high voltage through the very thin gas, and he could create illumination. He could create lights around the magnetic poles of his model. And from that, he assumed that it must be due to the Northern Lights must be due to electricity interacting with gases somewhere close to the Earth, and that magnetism played a very strong role. And that really is exactly right. And he theorized these must be tiny electrically charged particles arriving from space, causing the atmosphere to glow. And he was spot on. That's exactly what creates the Northern Lights. So he was also an interesting character, and when he was doing these experiments, he would have been aware that this kind of apparatus, this equipment, would have generated huge amounts of X-rays, and he was always conscious of the fact that the X-rays were coming out of his machine. So he always wore a fez on his head. You can see wearing fez in the laboratory. That little hat he liked to wear because he knew about the X-rays. So it was kind of very early health and safety. He was a bit of a character, Christian Birkeland. Now, what we understand today is if we look at the sun, it not necessarily the yellow-white disk that we see in the sky just outside our homes. And so here is a movie of the sun recorded from a spacecraft that is constantly staring at the sun with a very special camera that observes gases of various different temperatures emitting very, very high energy light, very high energy radiation. So this is the kind of light you can't see with your eyes. It's extreme ultraviolet light coming from gases at 1 to 2 million degrees Celsius. But you can see, if you look in this kind of image, you can see that the sun isn't uniform. There's lots of bright regions and dark regions. There is some activity going on. You can see these curved band-like structures around the active regions, which are actually magnetized regions of the surface of the sun. We can see the sun is rotating. It takes about 27 days to rotate once. It's a dynamic, crackling, energetic thing. It's not this just quiet, constant, uniform thing in the sky. And that activity doesn't just apply to the surface of the sun. If we stand back a bit and look at what we call a coronagraph, so this is a special camera that can look at the sun, and in the center there is a disk which blocks out the sun. And the really technical way to think about this is a bit like the sun visor in a car that you flap down to block out the sun so you're not dazzled by the sun. This camera has a special disk that obscures the sun, and the sun actually is where the white circle is in the middle. And it's constantly filming the sun, and we can see it's orbiting the sun, so the stars in the background are gently drifting past. But you can see this wispy material always streaming off from the sun, and that's the solar wind. It's the remnants of the solar atmosphere broken down into its electronically charged subatomic particles. So it's mainly hydrogen that's being ripped apart into protons and electrons, streaming out from the sun, about 1 million tons per second, streaming out into planetary space. And that's going on 24 hours a day, 7 days a week. And every now and again, there's a bit of a hiccup, a bit of a belch, and the sun fires out a burst of material into space. You can see every now and again, it looks like a puff of smoke in these movies, a little puff of smoke spat out into space. That's 1 billion tons of the solar atmosphere being fired out at 1 million miles an hour. And those can be fired off in any direction through the solar system. And this solar wind travels outwards and it arrives at the Earth a few days later, and it meets the Earth's magnetic field. So the magnetic field of the Earth is really strong. It acts like a magnetic force field, a bit like the shields on the Starship Enterprise. And so deep beneath our feet in the core of the planet, there's a molten core of nickel and iron. It churns around, generating a magnetic field, a bit like a dynamo, and it creates what we call a dipole shape. So it has two magnetic poles at the north and the south, and it's very similar to the shape you get if you do the science experiment in school, where if you take a magnet, put it under a piece of paper, sprinkle on some iron filings, it will trace out the shape of the magnetic field lines connecting the two poles, and you get this sort of shape. Well, this magnetic field acts as an obstacle. So in the magnetic field, in the material that streams outwards from the sun, I've got a nice cartoon here, from a nice graphic from NASA. The material streams out through space usually, and about 4 days later, solar wind material hits our force field, which we call the magnetosphere. It's the sphere of influence dominated by the Earth's magnetic field, and it goes around our planet and the magnetosphere, a bit like the river would flow around a rock. If you had a rock in a river, the river flows around the rock. In this case, the solar wind flows around the magnetosphere. But our force field isn't perfect, and some of the material leaks into the magnetosphere, and as well as that, the motion, the constant brushing past of the solar wind that is itself magnetized, carries the sun's magnetic field, couples into the Earth's magnetic field, and actually sets up this region to act a bit like a particle accelerator. It's a bit like the Large Hadron Collider at CERN. You have varying magnetic fields that pick up and move around electronically charged particles in the environment around the Earth, and can actually accelerate them to very high energies. And actually the Earth sits in the center of this natural particle accelerator that is fed by energy and material from the sun. And that's the source region of the aurora around our planet. And so if we take a view on the internet from the International Space Station, looking down at the Earth's atmosphere, you can see this thin carpet-like region of light that is the Northern Lights as the ISS orbits the planet. And what you're looking at there is a very thin layer of the Earth's upper atmosphere that's being bombarded from space by subatomic particles, mainly electrons. The electrons are running into gas atoms in the upper atmosphere, mainly oxygen and nitrogen, and causing them to glow. And so this glowing light we get in the night sky is entirely caused by electrically charged subatomic particles some of which originate from the upper atmosphere, some of which originate from the sun, being picked up, accelerated in our own natural planetary particle accelerator, fired into the upper atmosphere. And you can see these tendrils, these little wisps of material appearing to come up from the northern lights. That's actually the shape of the Earth's magnetic field line. And if I try and bring in my cartoon, if we think carefully about the shape of the Earth's magnetic field, in the polar regions, the magnetic field actually funnels material from space down into the upper atmosphere. So we tend to get the upper atmosphere in the polar regions glowing, which gives us the northern lights. And the physics that's going on is actually really common. If you see a sign in a shop window, a barber's shop window or a bar, if you look at a fluorescent lamp or a low energy light bulb, the light that's coming from that is caused by some atoms in a material being excited, being given extra energy, which makes them unstable. And they usually release that energy again as light. Now, in a neon lamp like this one, or neon lamps are actually usually sort of a rose orange color. This is full of xenon, this particular lamp. If you bombard xenon atoms or xenon atoms with energy, then and particles that are moving very fast, the xenon will gain some energy in the collision, and when it tries to release that energy to become more stable into a relaxed state, it emits blue light. Oxygen and nitrogen. Oxygen releases red light and green light. Nitrogen emits a pinky light. And so the red and the green and the pinky light we see in the northern lights, it's really like a neon lamp in the upper atmosphere, and the energy is coming from the space environment around our planet and ultimately the sun. And why do we see the northern lights where we see them? Well, if I bring together a couple of my previous images now, what you can see is that we have the Earth's magnetic field. It funnels material into the atmosphere in the polar regions, which is why we have the northern lights in the polar regions. And this all sits at the heart of a huge region of space we call the magnetosphere, which is doing all the particle acceleration for our natural light show in the sky. So where do you see the northern lights is often a question I often get asked. And there is... you can go and have a look and see where the northern lights occur most commonly. And this is a cartoon I borrowed from the internet. If you do a Google search for where can I see the northern lights, you'll probably find this cartoon. And it's probably not far off correct, actually. I think it's about right, having thought about it over many years. And what it tells you is in a region around the Arctic Circle, you will tend to see the northern lights on average for most nights. As long as it's dark. Remember that you need it to be dark to see the northern lights. And of course, at high latitudes in the Arctic Circle, we get very long summers where the sun never sets. So, but the aurora could be there. You just might not see them. And of course, clouds get in the way as well. But the northern lights are there most of the time. And actually, as you go further north towards the pole, the chance of seeing the northern lights drops off a little bit. But as you come away from that auroral oval towards the equator, say to where the UK is, it drops off very quickly. Now, I've just got some photos here just to prove that you can see the northern lights in a lot of different places. So Spitsbergen is Svalbard, which is in the high Arctic, 75 degrees north. You can, in sort of magnetic terms, you can see the northern lights there. And in Tromsø, that's slap bang in the Arctic Circle, great northern lights spot. Here are the northern lights over Lancaster a few years ago. So it does happen very occasionally, perhaps once or twice a decade. And here they are even further south, Colorado, USA, during a large solar storm in the early 2000s. So you can get to see the northern lights in lots of different places, but scientists like me generally go to the north where you see them most often, the Arctic Circle, and we use tools such as this. So these are two radars of the European Incoherent Scatter Radar Facility up in Tromsø in Norway. So these are enormous 32-meter dish antenna on the left and a big antenna about the size of a football field there on the right to study the northern lights with radio waves. One of the tools that we can use to diagnose the upper atmosphere. But as well as that, we use spacecraft orbiting the planet. We look at the sun. We get to go to some really exciting and extreme places because that's where scientists need to go to study the northern lights. So you know, people like me, really lucky, tend to think about scientists being stuck in laboratories and with white coats and crazy hair and melting ice in buckets and making things go bang. But actually, it can be much more fun than that. You can get to go to some really amazing places to study nature. And so in my case, I was lucky. I've been up to Svalbard a few times to study the northern lights. So that's where you have to go to work with a rifle, mainly as a big noisy stick to scare away the local population who like to come and see what you're up to. And so I've nearly finished now, but I'm just going to wrap up with you know, what are the chances of seeing the northern lights from here in the UK? Well, I've got two images here. One is of the northern lights in Finland on a particular occasion. I've forgotten the exact date, but basically this is a pretty normal aurora at the edge of the Arctic Circle. And here's an image taken from what is basically a weather satellite looking down at the Northern Lights. Don't worry about the color. The color is designed to look at clouds and things like that. So it's false color, but you can see the UK is down here. Scandinavia we have, and you can see the Northern Lights parked at sort of the edge of the Arctic Circle, which is where you'd normally see them. And someone here in Finland is looking north into the sky and seeing this. So this image was taken at about the same time as this one from the ground, from the space. Here we have an image taken, this one was in 2005. Here is that slightly blurry image taken by a colleague of mine, balanced on his wheelie bin at the bottom of his garden, I think, of the Northern Lights over the Lancaster University campus, which you can see glowing there in the M6 as it goes past the campus in Lancaster. And you can see the lights of the Northern Lights there, but you can see on the bottom, you can see this is an image from a weather satellite in space flying over at the time. And you see in that case, the Northern Lights have come much further south. And actually they're sat somewhere off the north coast of Scotland. And it's quite rare that they come that far south. And what we need really is the sun to be very active. And so the solar cycle is something that partly controls where the Northern Lights are. And what scientists have been able to do for hundreds of years is count the number of dark spots on the surface of the sun, because it tells us how magnetically active it is at the time, and keep a track of that over time. And if we do that, you can see that there is an 11-year cycle in solar activity and magnetic activity of the sun. And at the moment, we're at the bottom of it, pretty much, just starting to climb out. So the sun is very quiet at the moment. So although it's not impossible, the likelihood of the Northern Lights being seen over the UK are not so great at the moment. Give it a few years and we'll head back towards more active sun. The chances of solar storms pushing the Northern Lights down to us in the UK will increase a little bit. And then just to finalize, really, just to point out that the Earth isn't the only place that sees the Northern Lights. So here we have Aurora around the magnetic pole of Saturn. This is an image. So the images you're looking at there are taken from the Cassini spacecraft, which was orbiting Saturn, the planetary image. And then overlaid on that are images from the Hubble Space Telescope, looking in ultraviolet light again of auroral emissions around Saturn. And we know that Jupiter has aurora, Mars has some very faint aurora because it's not very magnetic. But across the solar system, we can look at different planets with magnetic fields, atmospheres, and we start to see the Northern Lights. So this is a process which we understand best at Earth, but we're now trying to map across to what we understand in the other planets as well. And so with that, I've probably muttered on far too long, so I'm just going to leave you with that beautiful picture of us searching for the Northern Lights here from Lancaster University. If you are interested in trying to see the Northern Lights from the UK, it's definitely worth a quick Google search. If you type Aurora Watch, just one word, Aurora Watch, into Google, you'll find our service which can send you alerts when there's geomagnetic activity that may highlight the Northern Lights to you in the UK. And I'll leave it there. So thank you very much for listening to me.
Jim, that was amazing. That was a really, really interesting presentation on Northern Lights. And honestly, well, speaking for myself, unfortunately, I didn't have the chance to see the Northern Lights as spectacularly as you showed. But the hint of over the horizon just got me excited. For actually seeing that beautiful phenomenon. So how long do we need to wait here in the UK to actually see the Northern Lights?
That's a really good question. So I'd like to think, do you know what, if I could predict the Northern Lights well, I'd be a very rich travel agent and not a scientist. So I think if you want to see the Northern Lights, you need several things. You first of all need the Northern Lights to be there, which is kind of obvious. I think they've got to be doing something. It's got to be dark. You've got to have no clouds, and you've also got to have a relatively dark sky in somewhere where you can see the northern horizon is what we'd usually say. Now, so whether or not the Northern Lights are there depends on a few things. But as I started to hint towards the end, at the moment, although the Northern Lights will still be there most of the time in the Arctic Circle, because that's their regular sort of stomping ground, that's where they kind of normally are, it's quite rare to get the geomagnetic activity that pushes it down as far south as the UK at the moment with the current level of solar activity. So at the moment, in terms of generation of the Northern Lights, we're at a bit of a low point. In the next 5 years, it will increase. Your chances will increase for seeing it at more southerly latitudes than you'd normally expect to see it. In terms of other things, though, even at the moment, if you went up to the Arctic Circle to see the Northern Lights, it would, this time of year in May, the sun doesn't set, so it's not dark enough. So you wouldn't get a very good view of it at the moment. So now in the Northern Hemisphere is not a very good time to be aurora chasing. As we get back around to the winter months and it starts getting darker again, you'd expect to start, seeing it up in Iceland, Norway, Canada, Alaska, all those kind of places, northern Scandinavia. You start to see that picking up again, and then the chances of it coming to the UK is probably going to pick up over the next few years. So you've got to be really patient in the UK. If you live in Scotland and you can easily see the northern sky, it's okay, but it's really difficult to kind of plan to go and see the Northern Lights from the UK. But there are lots of great places you can get to, and who knows, as the world opens up again for travel, I think a lot of people will be trying to see it.
Perfect. Thank you so much for that. Also, could you repeat the name of the medieval artist that created those beautiful pictures?
Okay, so I think the first one I had was the painting of the Northern Lights. It was it was Harold Moltke. So his name is spelled Harald Moltke, and he was a Danish painter and an author. And actually, he lived the end of I might have got the date wrong. It was the end of the 19th century into the early 20th century, and so he went to Greenland at about the turn of the 20th century and has done several well-known paintings of the aurora. The earlier stuff I was showing with the candles and things, that was actually, I can probably briefly show that if I just try and find it. That was unnamed because yeah, we weren't sure of the name on that one because it's just a little bit old. So it's an unnamed author. So there we an unnamed artist. So there we go. That was the picture of the sky lights in the night sky in the 1750s. So we're not so sure of who the author is on that one, who the artist is on that one. But certainly there we go. That one was a Danish painter, Harold Moltke, Moltke.
Brilliant. Thank you so much for that. Is there a sound associated with Aurora?
That's a really good question. Okay, so there are lots of reports of the aurora making sounds. However, as far as I'm aware, no one has ever recorded the sound convincingly and has demonstrated a mechanism that could make the sound. So I wouldn't like to say no, definitely not. But I think the jury is still out, and the verdict is unclear at the moment. If it were to make a sound, there would have to be some way of the sound getting from the aurora down to the ground. So the lowest aurora is about 100 kilometers. The highest is about 200 kilometers, and the distance, and that is a long way for sound to propagate. So it's not clear how that would happen. Nevertheless, there are a lot of people who insist that it does make a sound, either a hissing sound or a whooshing sound. Now, there are also some theories which say that the bits of the brain that processes optical information, it has a leak through to the bit of the brain that processes audio information. So I have seen discussed in some articles that if you're standing in a very quiet environment where there's not much noise, and you're looking at the Northern Lights, which is a beautiful optical display, you might get some leak through of the bit of your brain that's processing the optical side information might leak through into hearing, and you may perceive you hear something. But again, that's very hard to prove one way or the other. So the jury is still out, but it's very hard to come up with a realistic mechanism, some physics that would explain how sound would get from the aurora down to the ground to hear it. So I'm going to say the jury's out on that one.
So, I mean, if anyone from the audience is inspired enough to go and look for it, by all means, as you've heard, it's an open question. It's still an open question.
Very much so, yeah.
Now, well, the stars twinkle due to the atmosphere. Do the northern or southern lights twinkle as well?
Oh, that's a good question. That, do you know what? I've never been asked that one. So there should still be some shimmering effect because of the motion of the atmosphere, but the main motion of the northern lights, that sort of dancing light in the sky, is not due to the twinkling effect that you see for stars. It's actually due to the changing pattern of material coming down the Earth's magnetic field line from the space environment. So one way I sometimes think of the northern lights is if you imagine a bit of pavement or road and you've got a hose pipe. If you sprinkle water down onto the surface of the road, it will make a pattern on the road, and that's a bit like material coming down and landing on the upper atmosphere, causing it to glow. Depending on where the material arrives, it will cause different patterns in the to be illuminated. And so that movement effect that you see with northern lights is due to the processes in space firing material in changing over time. The regions where material is being fired in changes, the energy of particles coming in changes, the altitude at which those particles interact with the atmosphere changes just because of the energy that they're coming in with. So that changing pattern is not a shimmering like twinkling like starlight, but there will probably be a very small amount of that same effect going on as well. That's a really good question.
Brilliant. Thank you for the awesome answer. Now, is it easier to see the northern lights during winter, or is it just because the nights are longer?
Yeah, it is. It is really just that you've got the darkness. So even in the summer, the northern lights are there. And in fact, I showed at one point in my talk, I had a picture from a spacecraft using ultraviolet light. And one of the reasons we use ultraviolet light to study the northern lights from space is it doesn't matter about the illumination. It doesn't matter if you're looking at daylight or darkness, the daylit or the dark part of the Earth. You can do some clever image manipulation and still extract the glow of the aurora. And what we see is that the northern lights are there, whether we can see them or not. They're there all the time. And indeed, that ring goes all the way around the Earth. So if you think about that, that says that not only are they on the side of the Earth facing away from the sun, the nighttime, they're also on the side of the Earth facing the sun, the daytime. And you can actually get there are daytime aurora, but it's usually too dark to see them. But in the Arctic in the winter, when it's dark 24 hours a day, you can see the aurora at midday. So if you go to Svalbard, Spitsbergen, you can see the northern lights at midday. It doesn't need, because it's nighttime all the time. And so yeah, it's really just that it's the darkness of the sky allows you to see them, and sunlight obliterates the northern lights.
Perfect. Now, okay, that one is an interesting one. Is global warming affecting any way the northern lights?
Ooh, that's another really good question. Yeah. So how long have we got? So I think we know. Let me start that again. We can see that the changes in the upper atmosphere are happening because of changes to our climate. Now, what we can see, for example, there is something which is not the northern lights, but there is a phenomenon called a noctilucent cloud. And a noctilucent cloud is a cloud which is very high up in the very, very high altitude, many tens of kilometers up. And they're so high that after the sun has set where you are, because they're so high up in the sky, they're still illuminated from the sun, which is over the horizon, and they appear to glow in the night sky. And they're a very beautiful atmospheric cloud effect. And what we can see with those is the occurrence rate of those seems to be going up. We seem to be seeing more of them nowadays than people did 50 or 100 years ago. And yet they're a very obvious feature in the night sky, well, in the twilight sky. So it seems strange that no one would have reported them or observed them as much previously. And it looks like changes in atmospheric temperature and composition are starting to have an impact on that kind of phenomena. Now, the northern lights are a bit higher up. And so the temperature changes in the upper atmosphere may go down as well as up during climate change, due to depending on where you're looking, and the chemistry may well change. So at the moment, we're not seeing. I don't think we're seeing a massive impact of climate change, but I wouldn't like to rule it out, because we are going to subtly change probably the climate of the the temperature and the composition of the upper atmosphere. Certainly, there is also some very interesting links between climate and solar activity. I mentioned how the sun has an 11-year cycle in its activity. We know that drives auroral activity, that background level of solar magnetic activity. And that's known to have a little bit of an influence as well on how bright and how hot the sun is, but it's a very small change. So for a long time, climate scientists and modelers have already factored in the fact that the sun has an 11-year cycle of activity into climate models. So there's nothing terribly surprising there at the moment, I don't think, although it's always constantly being reviewed to seeing what's changing. So I think the answer is, at the moment, we're not seeing a climate change impact on the Northern Lights, but it's something we're looking at as the atmosphere changes slightly.
Brilliant. Let's close with a personal question to you. What is your favorite celestial object or phenomenon, and why?
Oh, that's a good one. That's a good one. Well, okay, so I think, unsurprisingly, I think the Northern Lights are one of my favorite. Well, probably my favorite, because I think not only because they're very beautiful and there's lots of legends and art about the Northern Lights, and I've got very fond personal memories. I remember the first time I saw the Northern Lights, I'll never forget it, in northern Norway, very, very cold, going and watching the Northern Lights, and it was amazing. But I think also they're very important for other reasons. So to get the Northern Lights, or to get the aurora on a planet, you need to have an atmosphere, really, and you need to have magnetic fields. So if you can look through a telescope at a distant planet, either in our solar system or in distant planets orbiting distant stars, it tells you that planet has a magnetic field, probably. It tells you it has an atmosphere. So it starts to give you clues about what's going on. So I just kind of think it's amazing that these beautiful lights in the sky with all these legends about the afterlife and spirits also can tell us about possibly environments on distant planets, and maybe even tell us if they're suitable for life on other planets. So I think they tick all the boxes.
Brilliant. And the last question that I would like to ask you, you said about aurora, right? Singular. What's the plural?
Okay, so technically, to be correct, the plural of an aurora are aurorae. So it's spelled slightly different with an extra e at the end, and so we would say, I have seen the aurorae on Saturn, Jupiter, and the Earth, but I have seen the aurora from Antarctica. So yeah, it's one of those interesting ones. It gets used differently all over the world, and even scientists whose job it has been for half a century to study the aurora or aurorae will have arguments in the pub about which one they should use correctly.
So, as your lovely feedback rolls in, I must say a big thank you to our moderators, Jamie and Diego. And of course, a huge thank you to Jim. There you go. Thank you again, Jim.
You're very welcome.
Thank you for watching, and I hope you enjoyed learning a little more about our amazing universe. Our team from Lancaster University also runs shows for schools, community groups and more, both in person with our portable inflatable planetarium and online. But any in-person events are subject to current COVID restrictions. If you're a teacher, community group leader or part of a similar educational organisation, please do get in touch. We're particularly keen to make connections with those in our region of Lancashire and Cumbria, but we'd love to hear from you wherever you are. But for now, take care and keep learning more about the amazing wonders of our night sky. Thank you.